Standing at the base of the Great Pyramid of Giza, it's almost impossible not to feel a sense of awe at this colossal structure, built over 4,500 years ago, stretches nearly 500 feet into the sky. Its stones, some weighing as much as 80 tons, fit together with precision that rivals modern engineering, and yet, the ancient Egyptians achieved this without cranes, without computers, without even the wheel as we know it. How did they do it? This question has puzzled historians, archaeologists, and engineers for centuries. The pyramids are more than just tombs. They're a testament to human ingenuity, a mystery carved in stone that refuses to give up all its secrets. Imagine the scene: thousands of workers laboring under the blistering sun, moving massive blocks across miles of desert with nothing but ropes, sledges, and sheer determination. There were no blueprints as we understand them today, no laser levels, no heavy machinery, and yet, the Great Pyramid sides align almost perfectly with the cardinal directions north, south, east, and west, with an error margin of just a fraction of a degree. How could a civilization so ancient achieve such staggering accuracy? The more you learn about the pyramids, the more the questions multiply. Were they using lost technologies? Did they possess knowledge we've yet to rediscover? Or was it simply the power of human collaboration on a scale we can hardly fathom today? This isn't just a story about stones and sand. It's about what happens when ambition, creativity, and perseverance collide. The pyramids stand as a silent challenge to our assumptions about the past, forcing us to rethink what ancient civilizations were truly capable of. And that's exactly what we're going to explore together. Over the course of this video, we'll piece together the clues left behind, the tools, the techniques, the ingenious solutions dreamed up by the Egyptians to uncover how they turned an impossible vision into a towering reality. So let's step back in time and walk alongside the builders of the pyramids, because their story is far more incredible than you might imagine. One of the most persistent myths about the pyramids is that they were built by slaves, an idea popularized by Hollywood and old textbooks. But modern archaeology tells a very different story. The real builders weren't whipped laborers under the lash of cruel taskmasters. They were skilled workers, well-fed and highly organized, who took pride in their craft. Recent discoveries at sites like Heit el-Ghurab, a workers' village near the Giza Plateau, reveal a community of artisans, stonemasons, and laborers who lived in purpose-built housing, not makeshift camp. These were not desperate souls driven by force, but dedicated teams working under what we might today call a state-sponsored project. The bones and remnants found in these villages paint a vivid picture. Workers enjoyed diets rich in meat, fish, and beer luxuries that wouldn't have been given to slaves. Archaeologists have uncovered evidence of cattle, sheep, and goat bones, along with bread and vegetables, showing these builders were fed like valued members of society. Some even received medical care. Skeletal remains show healed fractures, proof that injured workers were treated, not discarded. And here's something remarkable: grave goods buried with some workers suggest they held positions of respect, almost like modern-day engineers or foremen. So how did ancient Egypt mobilize such a workforce? Think of it like a national effort, a project so important that skilled laborers from across the kingdom were recruited, possibly in rotating shift. Records suggest workers were divided into crews with names like the Friends of Khufu or the Drunkards of Menkaure, hinting at camaraderie, even humor, among the teams. Seasonal labor likely played a role too, with farmers joining construction during the Nile's flood season when fields were underwater. Far from a top-down system of oppression, pyramid building may have functioned more like a shared cultural mission, one that offered steady work, good food, and a chance to contribute to something eternal. This changes everything we thought we knew. The pyramids weren't just monuments to pharaohs. They were built by communities, for communities. Every block laid was a collective achievement, a testament to what happens when skill, organization, and shared purpose come together. And that makes their achievement even more extraordinary. Cutting through solid rock to extract blocks weighing tons might seem impossible without modern machinery, but the ancient Egyptians turned quarrying into an art form. Their secret: a combination of simple tools, ingenious techniques, and sheer persistence. When workers approached a limestone quarry near Giza or the famed granite quarries of Aswan, they didn't have diamond-tipped drills or explosives, just dolerite hammerstones, copper chisels, and wooden wedges. These tools, though primitive by today's standards, were wielded with remarkable precision. Take the Aswan quarries, for example, where the iconic pink granite was sourced for obelisks and pyramid chambers. Workers first identified cracks or natural fissures in the bedrock, then used dolerite hammerstones, a type of volcanic rock harder than granite, to pound grooves along the desired cutting lines. Next came copper chisels, softer than stone but effective when combined with patience and water. By repeatedly striking the same groove while pouring water over it, they accelerated wear, gradually deepening the channel. For larger blocks, wooden wedges were inserted into these grooves and soaked with water. As the wood expanded, it exerted enough force to split the granite cleanly along the scored line. Limestone extraction followed a similar process, though the softer stone allowed for faster work. At Tura, near modern-day Cairo, workers carved trenches around blocks before prying them free with levers. The precision was astounding. Some quarry walls still bear the marks of these cuts, revealing how little material was wasted. But here's what's truly mind-blowing. Without advanced measuring tools, they managed to produce blocks of near identical size and shape, ensuring seamless fitting and construction. The real challenge wasn't just cutting the stone, it was moving these monstrous slabs. Once freed, blocks were dragged on sledges across carefully prepared pathways, often lubricated with water or mud to reduce friction. Ramps and rollers helped navigate uneven terrain, while teams of workers coordinated pulls with ropes made from papyrus or palm fiber. Every step, from quarry to construction site, was a feat of logistics, demanding not just muscle, but meticulous planning. What's often overlooked is the human element behind these techniques. Quarrying wasn't just about brute force. It required an intimate understanding of geology, an eye for natural weaknesses in the stone, and the ability to adapt on the fly. Mistakes weren't easily corrected. A misjudged strike could ruin a block meant for the pharaoh's burial chamber. Yet, the Egyptians worked with a confidence that suggests deep, hard-won knowledge passed down through generations. Their methods may seem rudimentary, but the results speak for themselves. Stone so precisely shaped that, even today, you can't slide a credit card between many of the pyramid's fitted blocks. Moving those colossal stones from quarry to construction site was a logistical puzzle the Egyptians solved with remarkable creativity. Without wheels or beasts of burden strong enough to haul such weight, they relied on a mix of simple physics and clever engineering. One key tool, the sledge, a flat, sturdy platform dragged by teams of workers. But pulling a sledge loaded with a 2.5-ton block across miles of desert sand would have been nearly impossible without a trick to reduce friction. Recent discoveries suggest they wetted the sand in front of these sledges. A wall painting in the tomb of Heit shows laborers pouring liquid in front of a massive statue being transported. An experiment by physicists confirmed that damp sand cuts pulling force by half. Too much water creates sticky mud, but the right amount forms a firm surface that prevents grains from piling up in front of the sledge, like sliding a sled over packed snow instead of loose powder. For heavier blocks, especially the granite used in pyramid chambers, evidence points to wooden rollers, not wheels, but cylindrical logs placed beneath the sled. As the sledge advanced, workers behind would rush to move the rear rollers to the front, creating a continuous rolling path. This method wasn't fast. Some estimates suggest just a few hundred feet per day, but with enough manpower and patience, even 80-ton stones could inch their way to the construction site. The Wadi al-Jarf papyrus, a 4,600-year-old administrative document, offers a rare glimpse into the scale of this operation. It records the shipment of limestone blocks from Tura to Giza, detailing the names of crews, the number of trips, and even daily quotas. One entry mentions a team called the escorters, delivering 200 blocks in a single month, proof of a highly organized supply chain. But here's the twist. Some theorists argue water played an even bigger role. The Nile's annual flood may have allowed barges to transport stones closer to the pyramid sites via temporary canals. A limestone block found near the Great Pyramid's base has traces of Nile clay, hinting at waterborne delivery. Others propose that during construction, the Egyptians built shallow harbors at the plateau's edge, using the floodwaters as a natural elevator to raise materials. What's often overlooked is the human coordination behind these methods. Moving a single block required precise teamwork, foremen directing pullers, workers adjusting rollers, and water carriers timing their pours. A misstep could mean injury or wasted effort, yet the system worked with staggering efficiency. The pyramids didn't rise by accident. They were the product of thousands of small, perfectly executed steps, each stone a testament to the power of collective ingenuity. Once the stones reached the pyramid's construction site, the next challenge was getting them into place hundreds of feet above the ground. How did workers lift blocks weighing several tons without cranes or pulleys? For decades, archaeologists have debated two main theories: the straight external ramp and the spiral internal ramp. Each has its merits, but recent discoveries might finally tip the scales toward one of them. The straight ramp theory, often depicted in textbooks, suggests workers built a massive, linear incline out of mud brick or compacted earth, extending from the ground to the pyramid's rising tiers. As construction progressed, the ramp would have been lengthened and heightened, creating a steady slope for sledges hauling stones upward. Proponents point to remnants of smaller ramps found near other Egyptian monuments, like the ruins of a zigzagging ramp at the Hatnub alabaster quarries. A straight ramp would have been straightforward to build, but here's the catch: as the pyramid grew taller, the ramp's volume would have dwarfed the pyramid itself. By the time workers reached the top, they'd have moved nearly as much material for the ramp as for the entire pyramid, a staggering inefficiency. That's where the spiral ramp theory comes in. Instead of one colossal straight slope, this idea proposes a winding ramp wrapping around the pyramid's exterior, like a ribbon corkscrewing upward. It would have required far less material, and workers could have adjusted its path as needed. But critics argue a spiraling ramp would have left little space to maneuver heavy blocks around tight corners, especially near the pyramid's apex. There's also no physical evidence of such a ramp, no surviving mud brick remnants or tool marks on the pyramid's faces. Then, in 2018, the ScanPyramids project made a breakthrough. Using advanced muon radiography, a kind of cosmic ray imaging, they detected a mysterious void deep inside the Great Pyramid, just above the Grand Gallery. This 30-meter-long chamber, nicknamed the Big Void, reignited the debate. Could it be part of an internal ramp system? French architect Jean-Pierre Houdin, a longtime advocate of the internal ramp theory, argues that this space might have served as a counterweight shaft, allowing workers to haul blocks upward through the pyramid's core while others descended, balancing the load. His model suggests a combination of external and internal ramps: a straight ramp for the lower levels, then a spiraling tunnel hidden within the pyramid's masonry for the upper section. Supporting this idea, microgravimetry scans have revealed density variations inside the pyramid patterns that could align with an internal ramp's pathway. Even more compelling are the notches found at the pyramid's corners, which Houdin interprets as docking points for temporary external ramps used to pivot blocks into the internal system. If he's right, the Egyptians engineered a solution that was both elegant and invisible, leaving no trace on the pyramid's pristine exterior, but the mystery isn't solved yet. Some researchers caution that the Big Void might have had a ritual purpose, not a practical one. Others propose hybrid theories, like a straight ramp supplemented by levers or counterweights. What's clear is that the pyramid's builders didn't rely on a single method. They adapted, innovated, and likely combined techniques in ways we're only beginning to understand. Every new discovery peels back another layer, revealing just how sophisticated ancient engineering truly was. The ancient Greeks might have left us one of the biggest pyramid building clues without even realizing it. Herodotus, writing almost 2,000 years after the Great Pyramid's completion, described a system of machines made from wooden levers that raised blocks step by step. Though his account was long dismissed as speculative after all, he was recounting stories told to him by priests centuries after the fact. Modern engineers are taking a second look. Could these machines have been sophisticated counterweight systems, harnessing basic physics to achieve what brute force alone couldn't? Picture this: a wooden beam pivoting on a stone fulcrum, with workers on one end and a granite block on the other. By shifting weights or adding manpower, they could have lifted blocks incrementally, like walking a heavy load up a staircase. Experimental archaeologist Denai Stocks tested this idea by recreating ancient Egyptian levers from timber and stone. His team found that with just 5 workers, they could lift a 2.5-ton block several feet in minutes. No pulleys, no wheels, just cleverly applied force. But the real game changer might have been combining levers with another innovation, the shadoof. This counterbalanced irrigation device, still used along the Nile today, operates on the same principle. A long pole with a weight on one end and a bucket on the other lets farmers lift heavy loads with minimal effort. Scale that up, and you've got a potential blueprint for pyramid construction. Teams could have used weighted beams to hoist blocks onto temporary platforms, then reposition the fulcrum to raise them higher in stages. Here's where it gets even more intriguing. Architect Jean-Pierre Houdin suggests the Grand Gallery inside the Great Pyramid wasn't just a passageway, it might have functioned as a giant counterweight shaft. His theory proposes that workers inside the gallery slid heavy stone weights down its corbelled ramps, using the downward force to lift blocks through an internal ramp system. This would explain the gallery's unusual sloping floor and the mysterious wooden notches found in its walls, which could have anchored ropes or pivot points. Supporting this idea, traces of where along the gallery's central walkway match the patterns you'd expect from repeated dragging of heavy loads. Even the pyramid's so-called relieving chambers above the king's chamber might have served as weight chambers, helping balance forces during lift. If correct, this system would have been a masterpiece of Bronze Age engineering, a hidden network of leverage and counterweights disguised within the pyramid's grandeur. Critics argue there's no direct archaeological proof for these devices. Wooden levers would have decayed over millennia, leaving little trace, yet the absence of evidence isn't evidence of absence. The Egyptians documented their religious rituals meticulously, but left few technical manuals. Perhaps they guarded their construction secrets as closely as modern corporations protect patents. What's undeniable is the result. Millions of tons of stone elevated with precision using nothing but simple machines and human ingenuity. Whether through levers, counterweights, or some hybrid system we've yet to uncover, the pyramid builders turned basic physics into a triumph of engineering. Their legacy isn't just in the stones they stacked, but in the boundless creativity they applied to conquer gravity itself. The precision of the pyramids isn't just impressive, it's almost supernatural. The Great Pyramid's north-south axis aligns with true north to within 0.05 degrees, a margin of error so tiny that modern architects would struggle to replicate it without satellite technology. To put that in perspective, even the most carefully constructed buildings today often deviate by at least a few tenths of a degree. So how did an ancient civilization, working millennia before the invention of the magnetic compass, achieve such pinpoint accuracy? The answer lies in their deep understanding of the stars and an ingenious tool called the Merkit. This simple yet revolutionary device, essentially a palm-sized notch stick with a dangling plumb line, doubled as both surveying tool and astronomical instrument. During the pyramid's construction, Egyptian astronomers likely used the Merkit to track the movements of specific stars, particularly those circling the celestial pole. By observing a star's rising and setting points over weeks or months, they could establish a precise north-south line. Here's how it worked. 2 Merkits were placed some distance apart, aligned with a chosen star like Polaris or Thuban, which served as the North Star in 500 BC. When both plumb lines cast identical shadows at a key moment in the star's transit, the Egyptians knew they'd found true north, but the Merkit was just one piece of the puzzle. Archaeologists believe the builders also used a technique called the Indian circle method, where they trace a circle around a central stake, then mark the points where a star's shadow touched the circumference at dusk and dawn. Bisecting the angle between those 2 points yielded a perfect north-south axis. This method explains why the pyramid's alignment is slightly off from modern magnetic north, because Earth's axis has shifted over millennia, altering the position of celestial reference point. The builders weren't wrong. they were working with a different sky. Even more astonishing is how this precision carried through to the pyramid's geometry. The sides aren't just aligned, they're nearly perfect isosceles triangles, with deviations of less than 2 inches across a base spanning 750 feet. Some researchers argue the Egyptians might have used standardized measuring rods or knotted ropes to maintain consistency, but others point to the pyramid's own shadow as a potential guide. During the equinoxes, the structure casts a shadow that, when bisected, creates a flawless east-west line. This level of accuracy wasn't just for show. In Egyptian cosmology, cardinal directions held deep spiritual meaning. Aligning the pyramid with cosmic forces ensured the pharaoh's soul could navigate the afterlife. Yet the practical implications are equally profound. Such precision allowed the pyramid's chambers to function as celestial calendars, with shafts pointing to specific stars used in rebirth rituals. The builders didn't separate science from spirituality, they fused them, creating a monument that was both mathematically precise and cosmically significant. What's often overlooked is the human skill behind these measurements. Without telescopes or digital theodolites, the Egyptians relied on naked eye astronomy, patience, and an almost obsessive attention to detail. A single misaligned merkit, or a shadow marked a few minutes too late, could throw off the entire structure. Yet they worked with a confidence that suggests generations of accumulated knowledge, passed down through apprenticeships we can only imagine. The pyramids stand as a testament not just to brute labor, but to the quiet, meticulous work of scholars and stargazers who turn the night sky into a blueprint for eternity. Before a single stone was laid for the Great Pyramid, the ancient Egyptians faced an engineering challenge that would make modern construction teams pause: how to level a 13-acre foundation on uneven desert bedrock with nothing but primitive tools. The solution they devised was so elegant that its traces can still be seen today. Archaeologists have found evidence of a grid-like network of shallow trenches cut into the Giza plateau, which researchers believe were filled with water to create a giant natural leveling system, an ancient version of what we now call a water table. Picture workers carefully digging narrow channels across the entire construction site, forming a checkerboard pattern. Once filled with Nile water, these trenches became liquid horizons, allowing surveyors to measure elevation differences with astonishing accuracy. Here's how it likely worked. Wooden measuring rods marked with consistent units were placed vertically at key points in the flooded trenches. By comparing the height of the water against the rods at various locations, teams could identify high spots in the bedrock that needed to be chiseled down or low areas requiring filler material. The principle was simple: water always seeks its own level, but the execution required painstaking effort. Evidence for this method comes from both archaeology and later historical accounts. The Greek historian Diodorus Siculus described seeing similar leveling techniques used in Egyptian construction centuries after the pyramids were built. Even more convincing are the tool marks and remnants of leveling lines found at the pyramid's base. Laser scans of the Giza plateau reveal that the foundation's corners vary by less than 2 centimeters in height across the entire structure, a margin tighter than many modern concrete slabs. What's often overlooked is the sheer scale of coordination this required. Teams would have worked simultaneously across the site, calling out measurements and adjustments in real time. Mistakes couldn't be corrected once the heavy stones were in place, so the foundation had to be flawless from the start. The Egyptians likely used knotted ropes or standardized wooden rulers to ensure consistency, but some researchers suggest they may have employed even more sophisticated tools. A few surviving artifacts resemble primitive sighting instruments, perhaps early versions of the tools that would later evolve into the surveyor's transit. The genius of this system wasn't just in its simplicity, but in how it turned natural elements into precision instruments. No lasers, no GPS, just water, wood, and human ingenuity converting the Nile's gift into a construction miracle. When the floodwaters receded and the trenches were filled in, what remained was a platform so perfectly flat that when the first cornerstone was laid, the pyramid's destiny as an architectural marvel was already assured. This level of preparation reveals something fundamental about the pyramid builders. They understood that true greatness begins from the ground up. The care taken in these initial stages set the standard for everything that followed, proving that the pyramid's perfection wasn't accidental, but the result of deliberate, meticulous planning. Every block that followed would rest on this foundation, both literally and philosophically, as the Egyptians transformed a patch of desert into a monument that would defy time itself. The Egyptians didn't have digital angle finders or laser levels, but they didn't need them. Their secret to achieving perfect right angles and vertical precision lay in two deceptively simple tools: the plumb bob and a rope knotted in the ratio of 3, 4, and 5. This combination, often called the Egyptian triangle, was their Bronze Age version of a carpenter's square, a geometric cheat code that turned basic materials into precision instruments. Imagine a worker standing at what would become the pyramid's corner, holding a length of rope divided into 12 equal segments by 11 knots, stretching 3 units along one side, 4 along another, and letting the remaining 5 form the diagonal. They create a perfect right angle every time. The math is unshakable. 3 squared plus 4 squared equals 5 squared. It's the Pythagorean theorem in action, centuries before Pythagoras was born. Archaeologists have found evidence of this technique in tomb paintings, and even in the wear patterns on surviving ropes. What's ingenious is how they scaled this method. By doubling or tripling the ratios 6, 8, 10, for example, they could verify larger angles without needing longer ropes. But right angles were only half the battle. Ensuring walls rose perfectly vertical required another tool, the plumb bob. A carved stone or metal weight tied to a string, it became the unchanging reference against gravity. Workers would hold it against a partially built wall, checking if the string aligned with markings carved into the foundation stones. The beauty of this system was its adaptability. If wind blew the string, they'd wait. If a stone protruded, they'd chip it down. The plumb bob didn't just measure, it enforced an unwavering standard, one that could be used at every stage of construction, from base to apex. Recent discoveries at the Red Pyramid of Dashur reveal how these techniques evolved. There, the lower courses show slight deviations, as if the builders were refining their methods in real time. By the time they reached the upper levels, the corners sharpened to near perfection, suggesting a learning curve etched in stone. Some corners even bear tiny chisel marks where workers adjusted stones by millimeters, like sculptors fine-tuning a masterpiece. What's often overlooked is the human intuition behind these tools. The Egyptian triangle only works if the ropes are taut and the knots perfectly spaced. The plumb bob is useless without a steady hand and a keen eye. These weren't just tools, they were partnerships between object and artisan, where skill turned simplicity into precision. The pyramids didn't rise because of magic or alien technology. They rose because generations of builders honed their craft, passing down tricks of the trade that turned geometry into something you could hold in your hands. This blend of math and practicality reveals a deeper truth about the Egyptians. They didn't separate theory from application. The same mind that calculated stellar alignments could knot a rope to square a foundation. In their world, the cosmic and the earthly were intertwined, and the proof is in the pyramids themselves, structures where every angle whispers of a civilization that saw no divide between the stars above and the stones beneath their feet. Of all the engineering marvels within the Great Pyramid, the King's Chamber stands apart not just for its purpose, but for the sheer audacity of its construction. The chamber's roof consists of 9 granite beams, each weighing a staggering 70 tons. To put that in perspective, that's heavier than a modern battle tank. These colossal slabs had to be raised over 150 feet above the pyramid's base and positioned with millimeter precision. And unlike the limestone used elsewhere, granite is brutally unforgiving, harder than steel, brittle under stress, and sourced from quarries hundreds of miles away in Aswan. Every step of this process, from transport to placement, pushed ancient engineering to its absolute limits. The first hurdle was getting these monolithic beams into position. Traditional ramps alone wouldn't suffice. Dragging 70 tons up even a gentle slope would require more manpower than the chamber's cramped space could accommodate. Archaeologists like Jean-Pierre Houdin propose a hybrid solution. an internal ramp system combined with lever and fulcrum techniques. Imagine workers inside the Grand Gallery using wooden beams as pivots, incrementally lifting each granite slab like a seesaw in slow motion. As one end of the beam was raised, wooden supports would be slid beneath it, allowing the other end to be hoisted in turn. This walking method, still used in some traditional stonemasonry today, could have elevated the beams step by step without requiring a massive workforce crammed into tight spaces. But lifting was only half the battle. Positioning the beams exactly where they needed to go demanded another ingenious trick: pivot points. The chamber's walls show where marks consistent with heavy loads being rotated into place. It's possible workers temporarily suspended the beams on rounded stone or wooden rollers, allowing them to be nudged sideways with levers once at the correct height. This would explain the chamber's unusually smooth floor, polished not for aesthetics, but to reduce friction during these microscopic adjustments. The margin for error was vanishingly small. A single misaligned beam could compromise the entire roof's structural integrity. The real stroke of genius, however, lies above the beams. 5 relieving chambers sit atop the king's chamber, distributing the weight of the pyramid's upper layers away from the ceiling below. This detail reveals a profound understanding of load dynamics. The Egyptians weren't just stacking stones, they were actively managing forces. Some researchers argue these chambers also served as counterweight spaces during construction, holding sandbags or stone weights that could be adjusted to balance loads during placement. What's often overlooked is the human cost of precision. Granite doesn't forgive mistakes. A slipped lever or a cracked beam meant months of labor lost. Yet the builders worked with a confidence that suggests trial and error elsewhere, perhaps in now lost training grounds or smaller prototypes. The king's chamber wasn't their first attempt. It was the culmination of generations of accumulated knowledge, where every scar on a quarry wall and every splintered lever taught them something new. This combination of brute strength and delicate finesse captures the essence of Egyptian engineering. They didn't just overcome obstacles, they turned them into opportunities to innovate. The king's chamber isn't just a room, it's a testament to what happens when necessity and creativity collide at the limits of human capability. When we think of the pyramids standing strong for over 4,500 years, we often picture those massive stone blocks fitting together like a perfect puzzle. But there's another unsung hero in this story, the mortar holding them together. Unlike modern cement, which cracks and degrades within decades, the ancient Egyptian mortar has endured millennia. Its exact recipe remains one of the unsolved mysteries of pyramid construction, yet recent scientific analysis has uncovered some startling clues about its durability. Take a closer look at the Great Pyramid's mortar joints, and you'll notice something odd. While the limestone blocks themselves have weathered and eroded in places, the mortar often appears smoother, almost glass-like. X-ray diffraction and chemical testing reveal it wasn't just simple lime plaster. The Egyptians mixed in unusual additives, including finely crushed silica, likely from desert sand, and traces of natron, a mineral salt used in mummification. Some samples even contain organic residues, hinting at plant-based binders like tree gum or animal glue. This combination didn't just harden, it reacted chemically over time, forming a crystalline structure that actually strengthens with age. The most baffling detail: modern engineers trying to recreate this mortar can't match its longevity. Lab experiments show that while the basic ingredients are replicable, something about the original mixing process, perhaps the exact temperature, humidity, or even the order of combining materials, gave it unique properties. One theory suggests the mortar was intentionally made slightly weaker than the surrounding stone, allowing it to absorb subtle shifts from earthquakes or thermal expansion without cracking. Another possibility is that the Egyptians exploited a natural reaction between the mortar and the pyramid's limestone, creating a self-healing effect where microscopic fissures seal themselves over centuries. But here's where it gets even more fascinating. The mortar wasn't used uniformly, its composition varies in different parts of the pyramid. Near the base, it's denser and more granular, likely to handle greater weight. Higher up, it becomes finer, almost powdery, possibly to reduce stress on upper blocks. Some sections contain traces of copper, which may have acted as an antifungal agent to prevent organic growth. This level of tailored engineering suggests the mortar was far more than just glue. It was a carefully calibrated component of the pyramid's structural integrity. What's often overlooked is the logistical challenge of producing this mortar on the scale required. Workers would have needed to grind silica to an impossibly fine consistency without modern mills, then transport natron from distant deposits near the Nile Delta. The mixing process itself might have been ritualistic. Wall paintings in the tomb of Rekhmire show laborers chanting as they prepare plaster, hinting that chemistry and ceremony were intertwined. The true genius of this mortar lies in its humility. Unlike the show-stopping stonework, it was never meant to be seen, yet its quiet resilience has outlasted empires, proving that sometimes the smallest details hold the biggest secrets. While we may never fully crack its recipe, one thing is clear: the pyramids stand today not just because of the stones, but because of the invisible bonds between them. Deep inside the Great Pyramid, hidden behind tons of limestone, lies a network of passages so precisely aligned with the stars that they functioned as a celestial time machine. The descending passage, a narrow corridor just 3.5 feet high and 3 feet wide, drops at a 26-degree angle straight into the bedrock beneath the pyramid. This isn't just a tunnel, it's a feat of engineering with astronomical significance. Carving such a passage through solid rock required more than brute force. It demanded an intimate understanding of geometry, astronomy, and the very movement of the Earth itself. The precision begins with the passage angle. 26 degrees might seem arbitrary, but it matches the latitude of Giza, meaning it points directly at the North Celestial Pole as it existed in 500 BCE. During construction, the pole star Thuban, not Polaris, as it is today, would have shone straight down this shaft like a cosmic spotlight. To achieve this, workers likely used a precursor to the Merkit, aligning the initial dig with the star's transit. But here's what's truly mind-bending: the passage doesn't waver. Over its 150-foot length, the deviation is less than 1/4 of an inch, a tolerance tighter than many modern laser-guided drills. How do they maintain such accuracy while tunneling through unpredictable bedrock? Evidence suggests they used a combination of fire setting and copper chisels. Workers would heat the limestone with controlled fires, then douse it with water or vinegar, causing thermal shock that weakened the stone. Once fractured, they pry out blocks with copper tools, inch by inch. Tool marks still visible on the walls reveal a rhythmic pattern: broad strokes for bulk removal, followed by meticulous polishing to maintain the exact angle. The ceiling's granite slabs, some weighing over 50 tons, were lowered into place using rope and lever systems, then sealed with that mysterious, long-lasting mortar. Yet the descending passage is just one piece of a larger celestial puzzle. Above it, the ascending passage and grand gallery form a vertical counterpart, aligned with Orion's belt during key dates in the Egyptian calendar. Some researchers believe these passages weren't just symbolic. They may have functioned as sighting tubes for ritual observations. During the summer solstice, sunlight would penetrate deeper into the passages than at any other time of year, possibly marking ceremonies tied to the Nile's flood cycle. The Queen's Chamber adds another layer of intrigue. Its 2 narrow shafts, long thought to be ventilation ducts, actually point to Sirius, the star linked to the goddess Isis, and Alpha Draconis, another pole star of the era. Recent robotic explorations found small copper fittings at the shaft's ends, suggesting they once held reflective surfaces to bounce starlight into the chamber. This transforms the pyramid from a static tomb into a dynamic observatory, where the heavens weren't just represented but actively interacted with. What's often overlooked is the human experience of these spaces. Crawling through the descending passage today, the air thick with 4 millennia of stillness, you can't help but feel the weight of the builder's intention. Every chisel mark, every polished surface speaks to a culture that saw no division between architecture and astronomy, between earth and sky. The pyramid's corridors aren't just passages, they're frozen equations in stone, capturing a moment when humanity first dared to map the cosmos in 3 dimensions. The night sky wasn't just a backdrop for the ancient Egyptians, it was their blueprint. When they aligned the pyramids with celestial bodies like Orion's belt, they weren't merely honoring the gods, they were encoding their cosmology into stone. The three stars of Orion's belt mirrored the layout of the Giza pyramids with uncanny precision, a connection that scholars believe tied the pharaoh's soul to Osiris, the god of rebirth who ruled the constellation. But this celestial map wasn't just symbolic, it was functional. By tracking Orion's movement across the sky, the Egyptians could predict the Nile's annual flood, the lifeblood of their civilization. One of their most ingenious tools for this celestial choreography was the Merkit, often called the world's first astronomical instrument. Picture a notched palm rod with a dangling plumb line held steady by a priest astronomer as he sighted the stars. But the real marvel was how they used it in tandem with another device, the bay, a forked stick that functioned like a primitive sextant. Together, these tools allowed them to measure the angular distance between stars with startling accuracy. On the desert plateau, they marked sight lines in the sand, creating temporary observatories where the horizon became their protractor. The solstices played a starring role in this cosmic drama. During the summer solstice, the sun would set exactly between the Great Pyramid's two smaller counterparts when viewed from the Sphinx, an alignment that may have marked the beginning of the agricultural cycle. Winter solstice observations were equally crucial. The sun's lowest point in the sky coincided with the start of the planting season. To track these events, the Egyptians developed the star clock, a system of decanal stars that rose roughly every 10 days throughout the year. Tomb ceilings from the Middle Kingdom depict these star tables, showing how priests could tell time at night by which constellation was vertical in the sky. What's often overlooked is the sheer patience required for these observations. Unlike modern astronomers with computerized telescopes, the Egyptians relied on generations of naked eye data, passed down through oral tradition and eventually recorded on temple walls. A single misaligned Merkit or a cloudy night could throw off months of calculations, yet their accumulated knowledge was so precise that when the pyramid's descending passage was sealed, it framed the pole star Thuban like a celestial bullseye, a snapshot of the heavens frozen in stone. The true brilliance of this system lies in its duality. The same stars that guided farmers also charted the pharaoh's path to immortality, weaving practical necessity and spiritual belief into a single cosmic tapestry. The pyramids weren't just tombs, they were stone telescopes aimed at eternity, built by a civilization that saw no boundary between earth and sky. Every alignment, every precisely angled shaft whispers the same truth. To the Egyptians, the universe wasn't out there, it was right here, etched into the very ground they walked on. The Nile River didn't just sustain ancient Egypt, it built the pyramids. Every year, like clockwork, the river's floodwaters submerged farmland for months, transforming the landscape into a shallow inland sea. But this wasn't a disaster, it was an opportunity. With fields underwater, millions of farmers suddenly found themselves unable to tend their crops, creating a vast seasonal labor force perfectly timed for pyramid construction. Instead of idle hands, Egypt gained an army of workers who could haul stone, mix mortar, or quarry limestone while waiting for the waters to recede. The flooding also supercharged logistics. During peak inundation, the Nile's tributaries stretched far beyond their banks, bringing water within mere miles of the Giza plateau. Archaeologists have uncovered ancient harbor basins and remnants of canals near the pyramids, suggesting builders used these temporary waterways to float stones right to the construction site. Imagine barges laden with the swan granite gliding across floodwaters that normally wouldn't reach the desert, their loads transferred onto sledges only for the final ascent. Even the heavy Chura limestone blocks, typically transported overland, may have taken seasonal river detours when floods opened new routes. Timing was everything. Papyrus records from the reign of Khufu mention deliveries of materials coinciding with the flood season, when the land is black and water covers the fields. Workers likely followed a cyclical rhythm, farming during the fertile months after the flood receded, then shifting to construction when the waters rose. This wasn't coerced labor, it was a symbiotic system where participation may have been framed as civic duty, even spiritual service. Farmers who helped build the pharaoh's tomb could expect blessings for their own afterlife, turning back-breaking labor into an act of devotion. The floods didn't just move stone, they shaped the pyramid's very design. Some researchers argue the stepped layers of early pyramids, like Djoser's, mirror the terrace basins Egyptians used to trap nutrient-rich silt during inundation. The Great Pyramid's smooth sides might symbolize the sun's rays piercing through floodwaters, a visual metaphor for rebirth. Even the construction schedule may have followed celestial flood markers. Sirius's heliacal rising heralded the Nile's rise, and pyramid shafts aligned with this star could have doubled as ceremonial calendars. What's often overlooked is how this system reveals the Egyptians' mastery of natural cycles. They didn't fight the flood's disruption, they harnessed it, turning a seasonal pause into productive power. The pyramids didn't rise in spite of the Nile's unpredictability, they rose because of it, a testament to a civilization that didn't just live with its environment, but thought in harmony with it. The same waters that grew their wheat lifted their stones, proving that sometimes the greatest engineering begins by working with nature's rhythm rather than against it. Behind every stone lifted at Giza stood an invisible machine more complex than any ramp or lever. The world's first civil service. The pyramid project didn't run on muscle alone, it thrived on meticulous bureaucracy, with layers of administrators ensuring everything from bread rations to granite deliveries arrived on schedule. At the top sat the vizier, the pharaoh's right hand, who functioned as both chief architect and CEO. Tomb paintings show these elite officials holding rolled papyri and scribble palettes, their shaven heads marking them as members of an intellectual class that could calculate material needs down the last barrel of Nile mud. A surviving document called the Diary of Mur offers an unprecedented look at this system in action. Mur, a middle-ranking official during Khufu's reign, kept daily logs tracking 200 workmen transporting limestone from Shura to Giza. His records read like a Bronze Age spreadsheet columns of hieratic script noting quantities moved, names of crew leaders, even daily weather conditions that might delay shipment. Every 10th day, these reports funneled upward to regional overseers, who compared them against master quotas etched into temple walls. Discrepancies triggered immediate investigations. A missing block wasn't just an accounting error, but a spiritual risk to the pyramid's perfection. The workforce was organized with military precision. At the base were laborers divided into crews of 40, each named after their foreman like the gang of the strong bull. Above them stood scribes like Mur, wielding reed pens instead of chisels. Their toolkit included cubit rods for measurement, clay tokens for inventory, and wax-coated writing boards for memos in the field. At construction sites, these scribes perched on limestone outcroppings, tallying deliveries against grid maps drawn on flattened ostraco pottery shards. What's remarkable is how they balanced rigidity with flexibility. When a sandstorm delayed one shipment, Murr's log shows workers from a completed quarry task immediately reassigned to ramp maintenance. This wasn't chaos, it was agile resource management centuries before the term existed. The system even had quality control. Inspectors used cord knotted at precise intervals to verify block dimensions, while scribes sampled mortar batches by pressing seals into wet plaster, creating time-stamped signatures. Far from the whips of Hollywood myth, motivation came through incentives. Workers accrued ivory tallies, the small notched sticks redeemable for extra beer rations or festival days off. The highest performing crews earned symbolic titles like Friends of Khufu, their names inscribed in barracks walls. Even accident reports show nuance. A broken limb might merit paid leave, while negligence cost ration privileges. This administrative web reveals the pyramid's true breakthrough wasn't engineering, but organization. Without computers or even paper, they coordinated tens of thousands moving millions of stones across decades, all while recording every load, every meal, every work shift. The stones may have been lifted by hand, but the project soared on the shoulders of history's first spreadsheet warriors. For decades, the only way to understand pyramid construction was through educated guesses until experimental archaeologists decided to put ancient techniques to the test. One of the most famous attempts unfolded in 1997, when a Nova documentary team teamed up with engineers and stonemasons to build a small-scale pyramid using only Bronze Age tools. Their project, set in the deserts of Arizona, became a real-world laboratory, revealing both the brilliance and the brutal challenges of ancient methods. The team started with quarrying a task that proved far harder than expected. Armed with replicas of dolerite hammerstones and copper chisels, modern workers struggled to extract even modest limestone blocks. After 8 hours of relentless pounding, they managed to free just one 2-ton stone, their hands blistered and tools dulled. The realization hit hard. What took the Nova crew days, Egyptian quarrymen accomplished daily, suggesting their techniques were more refined than anyone imagined. The secret, they discovered, wasn't just in the tools, but in the rhythm, alternating between hammerstones to exploit natural fissures, then inserting wooden wedges soaked overnight to quietly split the stone with expanding force. Transporting the block became the next hurdle. Inspired by tomb paintings, the team built a wooden sledge and loaded the stone atop it. But dragging it across dry sand required monstrous effort, 12 laborers straining just to move it a few feet. Then came the eureka moment. When they dampened the sand slightly, mimicking the Nile's annual flood, the sledge glided forward with half the effort. The moisture created a thin, firm layer that prevented sand grains from piling up, exactly as depicted in that ancient tomb painting. What seemed like a minor detail turned out to be a game changer. But the true test came with ramps. The team constructed a straight earthen ramp, only to watch it collapse under repeated use. Switching to a spiraling design, they faced another problem. Tight corners made maneuvering blocks nearly impossible. Their compromise, a hybrid system, straight ramps for lower levels, transitioning to lever-assisted lifts higher up. Using nothing but wooden beams and rope, they walked a 1-ton block up makeshift steps, inch by exhausting inch. The method worked but highlighted another insight. The Egyptians likely rotated crews to prevent fatigue, with fresh teams taking over every few hours. Perhaps the most humbling discovery was the time factor. The Nova team's miniature pyramid, just 20 feet tall, took weeks of backbreaking labor. Scaling that up to the Great Pyramid's 480 feet would have required not just thousands of workers, but generations of institutional knowledge. The experiment shattered myths while revealing new mysteries, like how workers maintained perfect angles without modern levels, or how they coordinated such a sprawling project without written blueprints. These modern attempts don't just replicate ancient methods, they spotlight the gaps in our understanding. For every technique the Nova team successfully recreated, a dozen questions remained unanswered. Yet each blistered palm and broken rope brings us closer to the truth. The pyramids weren't built by superhumans or aliens, but by ordinary people who turned ingenuity into stone. And that makes their achievement all the more extraordinary. Copper chisels shouldn't have worked on granite. That's the puzzle modern engineers still grapple with it. How metal softer than the stone it was meant to cut became the Egyptians' go-to tool for shaping some of the hardest rocks on Earth. The answer lies in a blend of patience, chemistry, and a little help from the desert itself. Granite ranks between 6 and 7 on the Mohs hardness scale, while copper barely reaches 3. Strike granite directly with a copper chisel, and the metal would crumple like foil, but the Egyptians didn't rely on brute force alone. Instead, they turned to an abrasive readily available in their environment, quartz sand. Crushed and sieved, this sand contained particles harder than granite, effectively acting as nature's diamond grit. Workers would sprinkle it along cutting lines, then drag copper tools back and forth like a saw, letting the sand do the real cutting. Over hours, sometimes days, the quartz particles embedded in the copper's edge would microscopically grind through the stone, millimeter by stubborn millimeter. But even with abrasives, copper tools had limits. Tomb paintings and archaeological finds reveal workers carried leather pouches of replacement chisels, suggesting they resharpened or swapped tools frequently. Metallurgical analysis of surviving copper chisels shows they were alloyed with small amounts of arsenic or tin, hardening them just enough to withstand repeated use. Yet the real innovation wasn't in the tools themselves, but in how they were maintained. At the Red Pyramid site, archaeologists uncovered flat stones with grooves consistent with tool sharpening, alongside fragments of quartzite hammers. Workers likely pounded and reshaped their chisels daily, keeping the edges fresh enough to hold abrasive particles effectively. The process wasn't fast. Experiments show that cutting a single granite block could take weeks of persistent effort, but speed wasn't the priority, precision was. The Egyptians compensated for their tools' limitations with meticulous planning. Quarry marks at Aswan reveal they often rough-cut blocks slightly oversized, then finish them on site with finer abrasives like emery powder. For intricate work, like the hieroglyphs in the king's chamber, they might have used copper drills tipped with sand slurry, rotating them with bowstrings to carve perfect circular grooves. What's often overlooked is the human element behind these techniques. Resharpening a copper chisel in the midday sun, or crouching for hours to guide a sand-loaded saw, required not just skill, but extraordinary stamina. The pyramids weren't built by magic tools, they were built by hands that knew how to coax miracles from humble materials. Every granite surface, polished to a mirror finish, stands as testament to a simple truth. Limitations don't define what's possible, they reveal what's inventive. Egypt's desert landscape presents a paradox when it comes to construction. How did a civilization with such scarce timber resources manage to lift millions of stone blocks hundreds of feet into the air? The answer might lie in an ingenious adaptation of one of their most vital agricultural tools, the shaduf. This simple counterbalanced lever, used for centuries to lift water from the Nile, could have been scaled up to become Egypt's version of a construction crane. But with wood being so precious, imported at great cost from Lebanon's cedar forests, every beam would have been used with surgical precision. Archaeologists have long debated whether full-scale wooden cranes existed at Giza. The evidence is tantalizing but fragmented. Tomb paintings from the Old Kingdom show workers using wooden levers to maneuver heavy statues, while pyramid texts mention great arms of acacia used in construction. The math is compelling. A shaduf-style crane with a 10-meter beam could theoretically lift a 2-ton block using just 4 counterweights and a handful of workers. But here's the catch: Egypt's native sycamore and acacia wood lacks the strength of European oak or Lebanese cedar. A crane capable of lifting the pyramid's heavier stones, like the 70-ton granite beams in the king's chamber, would have required timber thicker than most trees in the region. This scarcity forced the Egyptians to innovate. Recent excavations at the Heit el-Ghurab workers' settlement revealed something unexpected: stacked fragments of spliced timber, carefully joined with leather lashings and dowels. These weren't single massive beams, but composite structures, smaller pieces bound together to create load-bearing scaffolds. Imagine a network of these reinforced towers rising alongside the pyramid, each equipped with multiple shaduf mechanisms working in unison. Workers could have walked stones upward in stages, transferring them from one lever system to the next like a prehistoric bucket brigade. The real genius, however, might have been in the mobility of these cranes. Unlike fixed ramps, which required enormous material investments, wooden scaffolds could be dismantled and reused as construction progressed. Dendrochronology studies of rare surviving wood fragments show tool marks consistent with repeated assembly and disassembly. This recyclability would have been crucial given Egypt's limited forests. A single cedar beam might serve first as a crane arm, then become part of a temple roof, and finally end up as a noble's funeral boat, each phase of its life meticulously planned. Critics argue that no direct evidence of large cranes exists in pyramid reliefs or surviving artifacts. But absence doesn't equal impossibility. The Egyptians routinely depicted religious ceremonies in detail while omitting practical technologies, perhaps considering sacred imagery more worthy of preservation. Besides, wood decays. What remains for us to discover 4,500 years later are just stone foundations and metal fittings, silent hints of a sophisticated wooden infrastructure that vanished with time. What's certain is that every splinter of timber would have been accounted for, every lever stroke calculated. The pyramids didn't need European-style construction cranes, they needed solutions tailored to the materials at hand. Whether through shadufs, composite scaffolds, or some hybrid system we've yet to uncover, the builders transformed the humble lever into a tool that defied the desert's austerity. In a land where wood was rarer than gold, they proved that innovation isn't about what you have, it's about how you see what's already there. The pyramid's iconic shape wasn't just an architectural choice, it was a divine blueprint carved in stone. At the heart of this sacred geometry lies the benben, a pyramidal stone worshipped in Heliopolis, as the first land to emerge from the primordial waters of chaos. This mythic image, echoing the sun's rays piercing through clouds, became the spiritual template for every pyramid that followed. When a pharaoh's tomb rose in this form, it wasn't merely a building, it was a conduit between Earth and cosmos, engineered to transform mortal remains into celestial energy. Look closer at the Benben symbolism, and you'll discover layers of solar worship embedded in the pyramid's angles. The original Benben stone, kept in the Temple of Ra, was said to glow at dawn, a quality mirrored in how the Great Pyramid's polished white Tura limestone casing stones would have blazed under the Egyptian sun. These reflective surfaces weren't just for show, they turned the entire structure into a man-made mountain of light, visually fusing with the sun's descent at sunset. Even the pyramid's name, in ancient Egyptian Mer, literally means place of ascension, confirming its role as a launch point for the soul. The pharaoh's journey through these angles followed a precise celestial script. Ancient texts describe the deceased king transforming into a star god, climbing the pyramid's sloping sides like the sun god Ra scaled the sky. This explains why burial chambers were often positioned not at the base, but high within the structure. The higher the chamber, the shorter the souls climbed to the heavens. The pyramid's apex, sometimes capped with electrum, a gold-silver alloy, would have conducted lightning during storms, creating a literal connection between earth and sky that reinforced its sacred purpose. But the Benben connection goes deeper than shape alone. When archaeologists uncovered the earliest pyramid Djoser's step pyramid, they found its summit chamber contained a replica Benben stone. This suggests the entire monument functioned as an enlarged, walkable version of the sacred object, with each tier representing a stage in the pharaoh's transformation. Later smooth-sided pyramids like Khufu's refine this concept, their continuous slopes mimicking the concentrated energy of sunbeams. Even the pyramid's layout on the Giza plateau mirrors the stars of Orion's belt, turning the whole necropolis into a terrestrial constellation. What's striking is how this symbolism translated into practical construction. The same workers who aligned stones to stellar positions also carved hieroglyphs invoking the Benben's power. Foundation deposits beneath pyramid corners often included model tools and offerings not just for practicality, but to consecrate the site as holy ground. The pyramid was never just a tomb, it was a machine for resurrection, every inch calibrated to fulfill its cosmic purpose. When the last casing stone was placed, sealing the pharaoh within, the structure became frozen prayer, a permanent stairway waiting to carry its royal passenger home. This fusion of spiritual vision and engineering precision reveals the Egyptians' ultimate insight. Geometry wasn't just mathematics, it was theology written in stone. The pyramids didn't point the sky by accident. They charted a course the pharaoh's soul was meant to follow, each angle a runway for eternity. In a civilization where death was just another horizon, these monuments stood as beacons, guiding their kings not into darkness, but into everlasting light. The Meidum Pyramid stands today as a haunting silhouette, its collapsed outer layers forming a jagged tower surrounded by debris, a stark reminder that even the ancient Egyptians had to learn through trial and error. Originally built for Pharaoh Sneferu around 2600 BCE, this structure began as a step pyramid, much like Djoser's earlier monument. But Sneferu's architects attempted something revolutionary. They smoothed the steps into a true pyramid shape by adding outer casing stones. The result was catastrophic. Sometime after construction, possibly centuries later, the outer layers sheared away in a dramatic collapse, leaving the inner core exposed like a broken tooth. What went wrong? Modern engineers examining the ruins point to two critical flaws. First, the outer casing stones were laid at too steep an angle, creating instability as the weight pressed downward. Unlike the later pyramids at Giza, where careful calculations ensured each layer distributed the load evenly, Meidum's outer layers essentially slid off their own foundation. Second, the base wasn't properly leveled. Uneven settling of the ground beneath caused cracks to propagate through the masonry, weakening the entire structure. The lesson was brutal but clear. A pyramid's perfection depended not just on ambition, but on geometry and groundwork. Yet Meidum wasn't a total failure, it was a laboratory. Sneferu's engineers took these hard-earned lessons and applied them to their next project, the bent pyramid at Dashur. Here, they cautiously reduced the angle midway through construction when they noticed alarming stress fractures. The result, a pyramid that still stands today, its unusual shape a testament to real-time problem solving. By the time they built the Red Pyramid, Sneferu's final resting place, they perfected the formula, a gentler slope, precisely leveled foundations, encasing stones meticulously anchored to the core. The debris field around Meidum tells another story too, one of adaptation. Archaeologists have found evidence that workers salvaged fallen limestone blocks, repurposing them for nearby temples and later pyramids. Even in collapse, the Egyptians wasted nothing. This iterative approach reveals a culture that treated failure not as defeat, but as data. Each cracked stone and shifted foundation taught them something new, refining techniques that would culminate in the flawless geometry of the Great Pyramid. What's often overlooked is the human cost of these experiments. Meidum's collapse likely claimed lives, and the bent pyramid's mid-construction corrections would have required backbreaking labor to dismantle and rebuild sections. Yet the workers and engineers persisted, driven by a vision that transcended individual projects. The pyramids weren't just tombs, they were a dynasty's legacy, each one a stepping stone toward architectural immortality. Today, Meidum's ruins serve as a silent teacher. For every polished success of Giza, there was a Meidum, a bold attempt that didn't quite stick the landing. But without these so-called failures, the pyramids might never have reached their zenith. The ancient Egyptians understood something we often forget. Mastery isn't born from unbroken success, but from the courage to fail, learn, and build again. At the very peak of the Great Pyramid, where the four triangular faces should meet in a single point, there's something missing, the pyramidion, the sacred capstone that once crowned this architectural marvel. Unlike the massive stones below, this final piece was relatively small, estimated to be about 6 to 9 feet tall, but its absence leaves a gaping question: what was it made of, and why was it so significant? The leading theory points to electrum, a dazzling alloy of gold and silver that would have transformed the pyramid's apex into a blazing beacon under the Egyptian sun. Imagine sunlight striking this gilded pinnacle at dawn, its reflective surface igniting like a second sun over Giza. Electrum wasn't chosen at random, it held deep symbolic meaning. Gold represented the flesh of the gods, while silver evoked the bones of the divine. Together, they mirrored the duality of the pharaoh's nature, both mortal ruler and celestial being. Texts from the Pyramid Age describe the capstone as the benbenet, a feminine form of the sacred Benben stone, tying it directly to the creation myth where the first land emerged from primordial waters. This wasn't just decoration, it was the spiritual keystone, the final piece that activated the pyramid's power as a conduit between earth and heaven. But where did it go? Some scholars suggest it was looted in antiquity, stripped away by invaders or opportunistic thieves drawn by its precious metal. Others propose it might have been dismantled ceremonially, removed during a period of religious reform when solar worship shifted. There's even a tantalizing fringe theory that the capstone wasn't solid metal at all, but a hollow relic containing sacred text or ritual objects, explaining why no fragments have ever been found. The pyramidions' role likely extended beyond symbolism. Practical considerations come into play. Electrum, being highly conductive, could have acted as a lightning rod during storms, channeling divine energy into the structure. Ancient accounts describe the pyramid's apex glowing during thunderstorms, possibly from electrical discharges interacting with the metal. This phenomenon would have been interpreted as the pharaoh's soul communing with the gods, reinforcing the pyramid's function as a resurrection machine. Perhaps the most haunting clue comes from the pyramid texts, which speak of the capstone as the Eye of Horus, a protective seal guaranteeing the pharaoh's safe passage to the afterlife. Its absence today feels like a silent rupture in that ancient promise. Yet even without its crowning glory, the pyramid endures, a monument not just to what we know, but to the mysteries that still hover just beyond our grasp. The missing pyramidion isn't just a lost artifact, it's the whisper of a final secret, waiting at the apex of human achievement. Deep within the Great Pyramid's hidden passages, French architect Jean-Pierre Houdin believes he's uncovered one of ancient Egypt's best-kept secrets, a system of water-filled counterweight chambers that transform the pyramid's interior into a massive hydraulic lifting machine. At the heart of this theory lies the Grand Gallery, that soaring corridor with its towering corbelled walls. Houdin argues this space wasn't just a ceremonial pathway, but the operational core of an ingenious block hoisting mechanism. Imagine workers hauling massive limestone slabs up the pyramid's internal ramp system until they reached the gallery's base. Here, the real magic began. According to Houdin's model, teams would have suspended granite counterweights in vertical shafts, branching off the gallery, possibly the same mysterious voids detected by muon scans in recent years. These weights, likely stone-filled barges or containers, would float in water-filled chambers connected by narrow channels. When workers released a locking mechanism, the descending counterweight's force would be transferred through a network of ropes and pulleys, yanking the stone block upward along the gallery's central walkway. The gallery's unusual grooved floor and wall notches suddenly make sense in this context. They become tracks and anchor points for a synchronized lifting system. The beauty of this design lies in its efficiency. Unlike ramps requiring constant extension, the counterweight system could reuse the same water and weights for multiple lifts, minimizing energy waste. Workers wouldn't need to drag blocks vertically, they'd just guide them as hydraulic force did the heavy lifting. Even the pyramid's so-called relieving chambers above the king's chamber may have served as water reservoirs, their carefully engineered ceilings strong enough to hold thousands of gallons needed for repeated operation. Critics question why no water stains or erosion marks have been found, but Houdin counters that the system would have been temporary. Once construction finished, workers could drain and dismantle the hydraulic components, leaving only dry shafts that later archaeologists misinterpreted as symbolic passages. Supporting this, microgravimetry scans reveal unexpected density variations in the pyramid's lower chambers patterns consistent with stone that once sat submerged in water. The theory also explains logistical headaches. Moving 70-ton granite beams into the king's chamber using only ramps and levers would have required impossible manpower in such tight spaces. But water counterweights could generate tremendous force within confined areas, a principle Renaissance engineers later rediscovered. Hidden pulleys might explain the copper fittings found at the ends of the queen's chamber shafts, possibly serving as anchor points for auxiliary rope. What's striking is how this idea reframes the pyramid's brilliance. The Egyptians didn't just build upward, they engineered invisible systems within the structure itself, turning the very monument into its own construction tool. The Grand Gallery becomes a machine disguised as architecture, its true function concealed behind majestic proportions. If Houdin's right, the pyramids weren't just lifted stone by stone, they were raised by the intelligent harnessing of nature's forces, leaving no trace of their mechanical secrets behind. Beneath the Great Pyramid's towering mass lies a hidden world of sound, a network of chambers and passages that don't just echo, but transform noise into something otherworldly. The subterranean chamber, carved deep into the bedrock, holds a peculiar acoustic secret. When you clap your hands or chant inside its rough-hewn walls, the sound doesn't fade, it lingers, swirls, and amplifies in ways that defy the laws of ordinary acoustic. Researchers measuring these spaces have detected resonant frequencies between 60 and 120 Hz, a range that coincides with the natural rhythm of human brainwaves during meditative states. It's as if the chamber wasn't just built to be seen, but to be felt through vibration. This phenomenon isn't accidental. The Egyptians understood sound's power long before modern science confirmed its effect. Priests conducting rituals in these spaces would have experienced how certain tones seem to hang in the air, their voices merging with the stone's vibrations to create an immersive sensory experience. Experiments with replica chambers show that chanting the syllable a sound known to induce calm, triggers harmonic overtones in this frequency range, suggesting the pyramid might have functioned as a giant resonator. The Grand Gallery, with its corbelled ceiling, acts like a sound funnel, channeling vibrations upward toward the king's chamber in a cascade of amplified energy. But the real revelation comes from the materials themselves. The granite beams in the king's chamber contain high concentrations of quartz crystal, a mineral known to vibrate at precise frequencies under pressure. When sound waves from chanting or drumming passed through these stones, they could have generated subtle piezoelectric charges, creating an almost electric atmosphere. Modern studies of similar ancient sites, like Newgrange in Ireland, reveal that Neolithic builders also embedded quartz-rich stones in ritual spaces, hinting at a lost acoustic science shared across cultures. The pyramid's design takes this further. Narrow air shafts connecting inner chambers aren't just symbolic pathways for the soul, they're precisely sized to amplify specific frequencies. A vocalist standing in the queen's chamber can project sound through these shafts with eerie clarity, as if the stones themselves are singing, archaeoacoustic researchers like Stephen J. Waller have noted how the pyramid's dimensions match the wavelength of human vocal ranges, turning the entire structure into a kind of Bronze Age amplifier. What's often overlooked is the psychological impact of these acoustics. In dim torchlight, with sound waves ricocheting off polished limestone, participants in initiation rituals might have felt voices emanating from the walls themselves, a divine chorus echoing from the beyond. The pyramid didn't just house the dead, it brought the unseen to life through vibration, transforming ceremony into something tactile, immediate, and unforgettable. This interplay of architecture and acoustics reveals a civilization that didn't just build for the eyes, but for the ears and body. The stones don't just sit silently, they sing, and their song may have been the key to bridging the gap between the earthly and the eternal. In a world without electric light or amplification, the pyramids offered something just as powerful, a resonance that made the spiritual feel real and the impossible audible. The golden age of pyramid building didn't vanish overnight. It faded, one imperfect angle at a time. Take Snefru's bent pyramid at Dahshur, its awkwardly sloping sides a visible record of a civilization pushing its limits. What caused this architectural stumble? The answer lies in a perfect storm of dwindling resources, political shifts, and fading institutional knowledge. Unlike the Great Pyramid's flawless geometry, the bent pyramid's sudden mid-construction change from a 54 to 43-degree incline tells a story of crisis management. Cracks had begun spiderwebbing through its lower courses, forcing engineers to recalculate the entire design on the fly. This wasn't just an aesthetic compromise, it was a survival tactic, a desperate attempt to prevent total collapse. Behind this scramble lay deeper troubles. The once boundless supply of Tura limestone was strained from decades of quarrying. Transport routes grew longer as nearby sources depleted, stretching supply chains to breaking point. Papyrus records from Snefru's reign show increasing delays in material deliveries, with some quarry crews reassigned to repair crumbling temple complexes. Even the workforce had changed. Gone were the specialized crews of Khufu's era, replaced by smaller, less experienced teams. The meticulous accounting systems that once tracked every block now showed gaps, missing shipments, unfulfilled quotas, and scribble errors that would have been unthinkable a century earlier. Later pyramids like those of the 5th dynasties, Unas or Pepi Roman II, reveal an even starker decline. These structures stand barely half the height of their predecessors, their cores filled with rubble instead of precision cut stone. The casing stones, once polished to a mirror finish, now fit together crudely, their gaps patched with gypsum mortar. Even the sacred pyramid texts, once carved in deep, crisp hieroglyphs, appear shallow and rushed, as if the artisans no longer possessed the tools or time to execute them properly. What caused this erosion of expertise? Partly politics, as pharaonic power fragmented, centralized control over construction projects weakened. But there's another, often overlooked factor, the loss of master builders. The men who trained under Khufu's architects were aging, and their apprentices lacked decades of hands-on experience. Without written engineering manuals, knowledge lived in the hands and eyes of craftsmen. When the last stonemason who could align a passageway with Dubin died, that skill vanished with him. The ultimate irony, later pharaohs spent more resources maintaining crumbling pyramids than building new ones. Tax records show vast sums diverted to prop up sagging monuments. their foundations shifting in the unstable desert edges chosen out of necessity, not precision. The pyramids didn't just shrink, they became shadows of their former selves, their decline mirroring Egypt's own slow sunset from unmatched architectural titan to a civilization trying desperately to recapture past glory. Yet even in their fading, these later pyramids hold lessons. They remind us that no golden age lasts forever, and that even the grandest monuments are vulnerable to the slow erosion of time and neglect. The bent pyramid's awkward silhouette isn't just a failure, it's a testament to adaptability, a stubborn refusal to let ambition collapse under the weight of reality. And in that, it may be the most human of all Egypt's ancient wonders. From the precision of celestial alignments to the hidden engineering of hydraulic counterweights, the pyramids stand as a testament to what humans can achieve when brilliance meets persistence. We've journeyed through quarries where copper chisels met granite through sheer ingenuity, explored ramps that may have spiraled invisibly within the pyramid's core, and decoded administrative systems that orchestrated tens of thousands of workers with the efficiency of a modern corporation. Yet for every mystery we've unraveled, like the secret of sand-dampened sledges, or the celestial significance of the descending passage, dozens of questions remain. How exactly did they achieve that jaw-dropping alignment with true north? What undiscovered voids might still lie hidden beneath Giza's sands? And perhaps most tantalizing of all, what lost techniques have we yet to rediscover? The pyramids refuse to give up all their secrets, and that's exactly what keeps us coming back. Every new technology, from muon detectors to 3D modeling, peels back another layer, yet the deeper we dig, the more we realize how much we still don't know. That's the magic of these ancient wonders. They're not just static monuments, but living puzzles that evolve with each generation's curiosity. Maybe you're convinced by Jean-Pierre Houdin's internal ramp theory, or perhaps you think water-based levitation played a role after all. The Egyptians left us no blueprints, only clues scattered across tomb paintings and tool mark. So here's where the conversation turns to you. What unanswered questions about the pyramids fascinate you most? Have you ever stumbled upon a theory that made you see these structures in a new light? Drop your thoughts in the comments, whether you're a seasoned Egyptology enthusiast or someone who just fell down this rabbit hole today. Your perspective adds to the story. And if you're craving more deep dives into ancient mysteries, hit that subscribe button to join us as we keep exploring the past, one stone at a time. The pyramids waited 4,500 years for us to uncover their secrets. Who knows what we'll discover next?